You know that feeling when it seems like your application code and your database are speaking two totally different languages? Yeah, it's a classic problem. Today, we're going to dive into a really powerful tool that's designed to be the perfect translator, the UML Class Diagram. Think of it as the blueprint that can finally bridge that gap.
Okay, so to really get why this blueprint is so important, we first have to understand the core challenge, the thing that developers wrestle with every single day.
And here it is, the great divide. On one side, you've got your application code, which thinks in objects, these complex, interconnected things with behaviors and relationships. But on the other side, you've got your relational database. It doesn't think like that at all. It just thinks in flat, simple tables of rows and columns. This clash, often called the impedance mismatch, is exactly where a ton of bugs and complexity love to hide.
So how do we get these two different worlds to communicate without everything getting lost in translation? We need a single, unified blueprint, a universal translator that both sides can look at and understand. And that is precisely where UML class diagrams come into play, acting as this really elegant bridge.
So what is a UML class diagram really? Just think of it as the official architectural map for your data. It's a standard, part of the unified modeling language, that lets us see the entire system at a glance. We can see every piece, what information it's supposed to hold, and most importantly, how it all connects.
All right, let's open up the toolbox. If we're going to build one of these blueprints, we've got to understand the basic components. These are the real building blocks of our entire data structure.
The most important building block, the absolute cornerstone, is the class. Now, when we're talking about data modeling, a class is basically just a direct stand-in for a table in your database. It's an entity. So if you've got users, products, and orders, well, each one of those is a class. Simple as that.
And here's where it gets really practical. Each class maps directly to a database table. The class name, that becomes your table's name. The attributes inside it, those are just the columns. We even use these handy little notations called stereotypes, like PK for primary key and FK for foreign key, to spell out our unique IDs and how the tables link up. It's super clear.
Now, having a bunch of boxes on a screen is fine, but it doesn't really tell you a story, does it? The real magic, the thing that gives your whole system its structure, comes from defining the relationships between these classes.
First up, we have aggregation. This is what we call a has-a relationship, and you can spot it by the empty diamond shape. The key idea to remember here is independence. The classic example is a library that has books, right? But if the library closes down, the books themselves don't just puff out of existence. They can still exist on their own.
Now, let's contrast that with composition. This is a much, much stronger has-a relationship, and we show this one with a filled-in diamond. With composition, the part is completely dependent on the whole for its very existence. Think of a house and its rooms. A house has rooms, but if you demolish the house, well, the rooms are gone too. They can't just exist independently, floating in midair.
So you see the difference? It's a loose association versus a life-or-death dependency. And getting this distinction right is absolutely everything. This isn't just an academic exercise. This defines critical business rules and prevents data problems before a single line of code ever gets written. This is how you stop orphan data and weird logic errors right at the design stage.
So we've designed this beautiful, logical blueprint, awesome. But now for the most important part. How do we turn this drawing into an actual working database? Let's walk through that translation.
I mean, this is the key question, isn't it? How does this abstract picture on a screen become concrete tables and columns that can actually hold real data?
Well, luckily, the process is surprisingly straightforward. It's really just a simple three-step recipe. First, every class in your diagram becomes a table. Easy. Second, every attribute inside a class becomes a column in that table. And finally, all those relationships you drew become foreign keys, or if it's a really complex relationship, they might become their own special kind of table, called a junction table.
Theory is great, but let's make this way more concrete. We're going to walk through a case study based on our source material, designing a database for a university.
So it all translates just like you'd expect. The student class becomes a student table, professor becomes a professor table. But check this out. The really interesting bit is the many-to-many relationship. A student takes many courses, and a course has many students. How do you solve that? You create a new junction table right in the middle that just connects them. And notice the grade attribute. It doesn't belong just to the student or just to the course. It belongs to the combination of the two.
So it becomes a column right in that new junction table. It's a really elegant solution.
Now, if you've done any data modeling before, I know what you might be thinking. Hey, what about the classic ER diagrams? And that's a great question. So let's put UML head-to-head with the traditional approach.
The key difference really just boils down to focus. ER diagrams are data first. They were born and raised in the world of relational databases for database designers. UML, on the other hand, is object first. It comes from the world of software development. That's why UML has those richer relationship types we just talked about: aggregation, composition, and it can even model behavior, not just data. They're just built for slightly different primary audiences.
So, why would you pick UML? The biggest win, hands down, is creating that natural bridge between your code and the database. This is a huge deal for modern tools called object relational mappers. It means less manual work, less boilerplate code. You end up with one consistent language that your whole team can use, which cuts down on errors. And a lot of powerful tools can even auto-generate your database schema right from the diagram. Pretty cool.
But of course, let's be real, it's not a silver bullet. That same impedance mismatch can still make mapping really complex ideas from your code, like inheritance, pretty tricky. And for a super simple database, UML might just be overkill. And at its heart, it's an object-first point of view, which might not be what a pure data analyst is looking for.
Ultimately, what it all comes down to is this: there is no single best tool for every single job. The right choice always depends on your project's specific needs, your team's skills, and just how tightly you need your application code and your data model to be integrated.
And that leaves us with a final question for you to think about. Whether you're using UML, ER diagrams, or just some notes on a napkin, take a good look at your current project. Is your data model just a list of tables? Or is it a rich, expressive blueprint that truly captures all the rules and relationships of your system? Is it really telling the whole story?